Okay, so we are going to expand how we look at heat transfer. Like I said in 5.1, we are going to calculate how much energy is absorbed or released by a reaction a bunch of different ways. So 5.2, this is 5.2, sorry. If you are a textbook reader, 5.2 deals with what deals with molar enthalpy, or how many kilojoules or joules can be in a reaction per mole. Released or absorbed, doesn't matter. So again, it's difficult to, in an absolute way, measure every single thing that's going on in a reaction. There's actually something called entropy, or how much randomness is in a system. And some of the reactivity things, like how many electrons have to be lost or gained, all has to do with, it's really decided already by the chemical gods, right? How many valence electrons does it have? Is it a big atom? Is it a small atom? So in a relative way, in a practical way, we're going to study what is the delta H. We're going to call it delta H. What is the energy either absorbed or released when a system, whatever's happening, whether it's dissolving, melting, um, single displacement, combustion, whatever, changing from reactants to products. And what we're going to do today is we are going to put our system in some kind of surroundings and measure the change in the surroundings and relate it to the system. So molar enthalpy is the how much energy is either released or absorbed per mole of a substance. So we're going to describe the enthalpy change, whether we're talking about combustion, are we making a solution, are we melting something, are we freezing it. So in the most general way, we use this X is just sort of a descriptor. So we're going to use delta H comb, delta HF for fusion, delta HV for vaporization. You could put delta H mic. It really doesn't matter, okay? So one of the things about this unit that can be frustrating is the units. So when you see kilojoules or joules per mole, then that counts as molar enthalpy. And the reference values common reference values are on page 307. So again, somebody might have put a sticky in there, just leave it in there. And so when you go to do the homework, it can be a tiny bit frustrating from the textbook because they're going to expect you to go look up the molar enthalpy. Same thing with a specific heat capacity value. It might not give it to you. Those are the ones that are on page 306. If you have joules and you have to change it into kilojoules, so what you can do is dimensional analysis where you cross out units and see what you're left with. Sometimes if I want something to work out to a certain amount, your answer might be in joules, and I might say put your answer in kilojoules as like an extra mark. If I don't say that and your answer just works out to be in joules, you can just leave it in joules, okay? But if you have to change it, then you do joules divided by 1,000 gets to kilojoules. And then vice versa. So if you have a question and you're given heat capacity in joules and the Q value in kilojoules or something like that, you have to make sure your units match. So we're going to use molar enthalpy, kilojoules or joules per mole. We're going to use enthalpy change, which is just kilojoules or joules, not per mole. And we're also going to use the sign, whether it's negative or positive, to indicate whether energy is being absorbed or released. So endothermic processes, we already talked about that energy is gained by the system, or the delta H of the system has increased. Mathematically, this is the best way to tell. Delta H is going to be a positive value. So whether you do a calorimeter question like we're going to do today, Hess's law, enthalpies of formation, any of the calculations throughout this unit, if you get a positive delta H value, that means it's an endothermic process. So exothermic, remember if you like a cutesy way to remember them, heat is exiting the system. Exothermic, delta H is negative. Okay, so tonight when you go to sleep, or Sunday night before you come back, or Monday night before you come back to class on the Tuesday, you'll say delta H is positive, it's endo, delta H negative is exo, over and over and over again until someone comes to you and says, can you please be quiet and go to sleep, okay? It's so important to remember that positive and negative don't necessarily mean like moving one way or another on a number line here. Because we're going to look at the size of the number. So this 241.8 kilojoules is more energy than 23.6 kilojoules. This doesn't mean negative like in a bad way. What it means is this is actually better. More energy is being released. Releasing energy is what we call thermodynamically favorable, right? Then we can use that energy for something else. Versus this, whatever this reaction is, 23.6 kilojoules have to be used. So endothermic, which means you would have to plug it in, heat it up, whatever. So that's called thermodynamically unfavorable. So again, not that a paper and pencil task, I could get you to do whatever I wanted, right? However, in a practical way, most of the questions you're going to do will be exothermic because that makes more sense. A chemical reaction, if it requires energy, then that, generally speaking, would be more difficult to do. So you'll see more of the questions are usually negative, give you a negative value instead of a positive value. Okay, so the first kind of calculation you can do with molar enthalpies is this one here. Okay, so if you're finding the enthalpy change, or how much energy is released or absorbed by a reaction, molar enthalpy is often a reference value, or we're going to calculate it today using calorimetry by the end. So it's the formula listed there, delta H equals moles times delta HX, is actually, you can actually practically think about what it means. So if you have on page 307, it says melting water releases or requires 6.03 kilojoules of energy per mole, and you have 5 moles. What would you do with that? Oh, I've got 5 times the amount of moles. I'm going to multiply and get 5 times the amount of energy. So that's what this formula is doing. So if you like dimensional analysis, then these formulas will, if you keep the units in your answer, then it'll help you figure out, like you can cross them out and figure out what your unit should be. So again, this X here can be anything. We're just describing the reaction. So delta H comb, delta H solution, delta H neut for neutralization, delta H Sean. It doesn't matter. It can be whatever you want. But the important thing here is that if it's kilojoules or joules per mole, then that is molar enthalpy. So when you multiply moles by kilojoules per mole, the moles cancel out, and you're left with kilojoules, which is what delta H is. Just in case you need a refresher, when you calculate moles, if you have a solid, then it's mass over molar mass. Whereas when you calculate moles for a solution, and we're going to do both, it's concentration times volume. So it's the same basic idea when you have a formula. So you could be given or asked to go look up what the reference value is for the molar enthalpy, and the question would say, what's the enthalpy change? So then you'd have to be given moles or grams and calculate it, or concentration to calculate it. Then you could do moles times the molar enthalpy. You could be asked for the molar enthalpy, but then you would have to be given enthalpy change, and you would divide by the number of moles. So it's the same basic idea. Three variables you would need to be given or be able to look up 2 unknowns. Okay, so in the first lesson, we did Q equals MC delta T, so where the temperature changed. And then there was this picture like this. So this would be where the temperature is changing. But now, what if there is no delta T? So this is where we would use the molar enthalpy value when you can't do this. Okay? So in these questions, it's if you're using the molar enthalpy of for the melting point or vaporization, which is boiling point. So there's two columns. There's two columns in the chart, one for melting, one for vaporization. And so but it's the same formula, you just have to look up the value. Why they can't just use the word melting instead of fusion, I don't know, but it's called the molar enthalpy of fusion, or the heat of fusion. So we use F. So this is the same formula as before, but instead of X, now we've written what the reaction is we are describing. So this formula represents the energy required to change a mole of solid into liquid. So if you're finding the molar enthalpy, then it's kilojoules per mole, which is what the textbook gives you. And so in the table, all of the values are listed as positive. So that is solid into liquid. So if you think about it, if you are going to melt something, change it from a solid to a liquid, you have to put energy in. So all the delta H values are positive. Because of the law that energy can't be created or destroyed, then if you're going to go the other way, so you're going to change a liquid into a solid, you're going to freeze it, then you would have the same value. The amount of energy would be the same because we're going to follow the laws of thermodynamics, but the sign would be negative because now your energy would be released. So the only annoying part is if you get a question that talks about freezing, for example, then your answer will be right, but your sign will be wrong, and then you'll be like, oh, I just had to change the sign of the reference value, okay? That's just a little weird trick to it, I guess. So then the same principles will be true for the next change of state. Now we call it vaporization. For boiling point, again, no delta T, so still at those plateaus. So we can't use Q equals MC delta T. So we're going to use the molar enthalpy formula. So changing a liquid into a gas requires energy. So all of the values listed are positive. If you were going to do the reverse change, so condensation, like changing a gas into a liquid, it would have the same amount of energy, but the sign would be negative. Most of the time, you can just use the value that's in the book straight up, but just in case, there's a little trick to it. Okay, so it says what kind of example it is. So we're going to do the heat transfer or enthalpy change for a change of state. So it says, unfortunately, one of the weird things is sometimes they use the words interchangeably. Okay? Basically, how much energy? How much energy is required to melt 100 grams of ice? So it looks like we're only given one piece of information, right? The grams. There is an important piece of information we are not given. So even if you forget that melting is a change of state, there's no delta T or no TF and TI, no final and no temperature given really at all, right? But we need something else. So if we're going to do enthalpy change, like how much energy is lost or gained, then we need some kind of enthalpy value. So if you're not using delta T, then you're going to use the molar enthalpy. Another thing, try not to be your own worst enemy. It does say ice. What is ice? Water, okay? So in the table, it doesn't say ice. And so many times students are like, Miss Todd, ice isn't in the table. And you're so good at the hard things, that you're forgetting about the easy things, okay? So we need the reference value. So a few ways to think of this. You can think of it like no delta T. You can think of it like this is a change of state, which means I'm going to use fusion or vaporization. Or once there is no delta T, then you're going to use the molar enthalpy, whatever works for you. And again, unfortunately, instead of just calling it delta H for melting, they call it delta H fusion. And it's on page 307, right in the book, okay? So you do need to change, we can't use grams, we need moles. Grams is a solid, so we can do the solid way. So in this unit, you're going to get a periodic table as reference information, and you're going to get, um, I basically printed off your textbook. You need specific heat capacities, molar enthalpies. Eventually, we're going to get to molar enthalpies of formation. So there's quite a bit of reference information that is required, okay? So hydrogen rounds to 1, the atomic mass. So 2, oxygen is 16, so that's going to be 18. I don't normally, especially on a paper pencil task, worrying about significant digits, you don't really have to do that. I'm just going to round to 2 decimal places. So again, if you think about what the reference value means, 6.03 kilojoules for 1 mole. If I have 5-ish moles, then I'm going to need 5 times the amount of energy. So my number should get bigger, okay? Or you can memorize the formula, or you can do dimensional analysis. You can continue and always put X if you want, or you can put like what it is. So this is fusion. I'm going to keep the units through my calculations so I can show you how to cross them out. You don't have to do that, but you do have to make sure you have the right units in your answer. Okay, so mole on the top, divide by mole or mole on the bottom, so they cancel out. And you're left with kilojoules. So sometimes this would be like part A. Part B would say, is it endo or exothermic? So you could talk about melting requires energy, and now you know that if the delta H value is positive, that also means endothermic. Okay, so there's a mathematical way now also to describe what's happening. Yes. Yeah, so I literally, I don't know if you can tell, but it's like I printed out your textbook. So you would definitely get that. You do not need to memorize those values. Now, you might find, to be honest, that once you do a bunch of these questions, you'll be like, oh, I have these reference values memorized, but you don't have to. Okay, so what happens if we want to get a little bit more complicated? So we can use something called a calorimeter that will insulate or separate the system and the surroundings from the environment. So when we do the lab, on the Tuesday you come back, we're going to use coffee cups, and you're going to use water, and then you're going to put your system in and close the coffee cup really quickly. And as long as you keep your cups together, it obviously, you know, if we left it for 24 hours, yes, right, the coffee would, if there was coffee, would not stay cold, I mean hot. So the reaction should take only a couple of minutes, maybe not even a minute. You'll monitor the temperature change, and then we're going to use the system and relate it to the surroundings. So if we are following the law of thermodynamics, and like I said, you guys, usually we do 3 of these labs, the same basic procedure, and by the time we get to the 3rd lab, students often get like 0.6% error, 1% error, and that never happens in experiments, right? Where you're so close to being correct. So this is easy to prove that the system, if it releases energy, where does it go? Into the surroundings. If the system needs energy, where does it get it from? It gets it from the surroundings. So we usually use distilled water that's readily available, and it's easy to measure the temperature change of the water. We can't easily put our thermometer in between the 2 little reacting particles, so we can say, okay, the temperature of the water went up by 10 degrees Celsius. That means, why? Where did it get that energy from? It got it from the reacting system. The system reacting or changing state released energy. So the lab we're going to do on the Tuesday mimics those ice packs or hot packs where you crack them. So you're mixing a salt. So we're going to use various ionic compounds with water. Sometimes the dissolving process absorbs energy. which makes a cold pack, and sometimes the process releases energy, which makes a warm pack. It makes it hotter for whatever kind of injury you have. Okay? So this slide is basically saying what I just said in words. Okay? So if we're going to follow the laws of thermodynamics, and I know sometimes in science we're like, oh, the exceptions. No, this is easily proven. Okay? So the change in energy in the universe is zero. Energy cannot be created or destroyed. So if you can have a system in a surroundings and it is not interacting with the environment, so we're not going to put stuff in our coffee cups and walk around and say, hey, do you think this is real coffee? No. We're going to insulate it from the classroom. Then whatever energy is lost or gained by the system is going to be equal to whatever energy is gained or lost by the surroundings. So if the system gains energy, it took it from the surroundings. If the system releases energy, it gives it to the surroundings. So the way that we mathematically do that, because now you know positive is gaining, negative is releasing, if they're equal but opposite signs, then we can calculate the using the delta T, we can calculate the enthalpy change in the system without having to put a thermometer in between the little reacting particles. So we can measure the delta T of the surroundings. So on the surrounding side, we're going to use MC delta T. Then on the system side, we can't measure the internal energy using a thermometer. It's just not possible. So no delta T. So again, in any case, whether it's change of state or something like this, when there's no delta T, you can use this relationship, and we're going to put them together. So when I do the examples, we're gonna talk about the system side and write about it, and the surrounding side, and then I'm gonna put it together. Some students choose to keep it separate and then relate it at the end. There are options here. But the big thing is, especially if you want your math to work out, that it's delta H system equals negative Q of the surroundings. So if you keep the negative side here, then it will, and you do your math correctly, like final minus initial temperature, then your answer should be the correct sign. If the system is an endothermic process, your answer will come out positive. If your system is an exothermic process, it'll come out negative. If you prefer to be a visual learner, the next slide is just a visual representation of it. And on the next slide, did it print in color? Oh, it did. Okay, so if you didn't print in color, you might want to, even if you have something blue, so we can represent the water, if you print it in color, then it will be fine. But Okay, so eventually when we get to 5.3, we are also going to relate potential energy and kinetic energy again. But so energy is, or kinetic energy is the energy of motion. Potential energy is stored like in bonds. It doesn't have to be in chemical bonds necessarily, but for us, that's what it is. This picture is representative of the system has high energy stored in its bonds. It's got a high potential to do work. And then the surroundings it's in, so the water, we're going to measure the kinetic energy. That's temperature. Okay, so we can measure the temperature of the water. So again, this line is blue to signify the water. Then, so this is the surrounding. And this is the system. So as whatever is occurring, whether it's melting, dissolving, freezing, vaporization, neutralization, single displacement, doesn't matter. Whatever's happening with the system starts to happen, and then it's releasing the energy, and then it ends up with low energy because it's given it all away. But where did it go? This is the water is cool, and then it starts to increase in temperature because it's gaining energy from the system. Please note that this line doesn't go to zero. According, everything has to be moving, or the thread of a black hole is imminent. So when we eventually do these pictures, don't make your lines go all the way to the x-axis, okay? That defies the laws of physics. And these lines are equally spaced apart, okay? So whatever the system has, it's going to give it away, and that means that if it's exothermic, and that means this surroundings is going to gain it. So endothermic would be the same but opposite. The system would have low potential energy, and the water would be up here, and then the system would take energy or absorb energy from the surroundings and then have higher. So that visualizing it is what we're going to do when we get to 5.3. I just noticed, I don't know if your printers did this, but my printer cut the titles off, but only the top. Did it do that to you guys? Oh, that's weird. So if like mine cut this off, this top one, so you might need to write that down. The good news is with the questions, so we're basically going to do different procedures to find delta H, but the question is usually very specific. Using a calorimeter, calculate delta H. Using Hess's law, calculate delta H. Using standard enthalpies of formation, calculate delta H. So if you have to really read the questions carefully, but it will give you a clue about what you're doing, okay? So a calorimeter has to have a system and a surroundings, okay? It is closed because we don't want energy transfer with the environment. So we're going to, whatever the system is, you can do either. You could do reaction, you could do dissolving, you could do melting, it doesn't matter. And then you can use the temperature change as a clue to whether the reaction's endo or exothermic. You could also use the sign of delta H. That's a terrible triangle, sorry. Okay, so one weird thing about this is it does say that surroundings is the water in the calorimeter. So even if you have a solid and water, that's obvious. When we do an example with solutions, so even though solutions, you might think that a solution isn't water, which is true. However, dissolving something in water to make an aqueous solution, that is a physical change. So what that means is you could evaporate the water and get it back. So then we consider a solution that's dilute enough to be an aqueous solution, which means no precipitate in it. We say that it has the same properties as water. And let's see. So yesterday we did those demonstrations, and now these petri dishes are empty, evaporated. Okay, so there are many properties of water. The ones we need, the specific heat capacity. So in your, often it'll say in the question, assume the same specific heat capacity as water. It says that here on your worksheet, okay? If you try to go look up the heat capacity of, let's say, hydrochloric acid, which is a common solution you'll use, then if you try to go look it up, you won't find one because it wants you to use waters. This property is from grade 11. 1 milliliter of water is equal to 1 gram. Okay, so we're gonna need that because when we do Q equals M C delta T, the M we're talking about is actually milliliters of water. They're the same because water's density is 1. Okay, so we're going to draw 2 pictures to help us visualize what's going on. I think, yeah, this title's okay. So using a calorimeter to estimate delta H for a change which involves a solid system. So if you have the notes printed off, there's 2 blocks. One of them is a solid, the other one is an aqueous system. So just make sure you're doing the solid system first. Okay, so draw a calorimeter. Please don't judge my artistic skills. A calorimeter, we want it to have a closed lid. The surroundings will be water, so draw some water. And then draw some sort of system. You can draw whatever you want. It could be dissolving, it could be reacting with each other inside water, it doesn't really matter. So it does need to be contained in the surroundings. Like when we do the lab on Tuesday, you might have to gently mix with your thermometer, okay? You can't let the solid sit on the top of the water. So again, when you have a solid, moles is mass over molar mass. The surroundings, you'll probably be given the volume of water, which is equal to the grams. Okay, so what I'm going to do is I'm going to write some notes about how the temperature is going to change. So these temperature change notes are going to apply to the chemical one as well. So if you have more space, like if you're out of space in this box and you want to sort of write them in the box beside it, that's okay. It's going to apply to both. Okay? So the temperature is going to change. So let's say 50-50, right? Temperature goes up, temperature goes down. There's only two choices. So what you're going to do is make observations about the system, or the surroundings, sorry, whether it's on a paper and pencil task or in a lab, but you're going to note the temperature change. Does the temperature go up or increase, or does it go down or decrease? So if the temperature of the surroundings increases, that means that the system released energy. So when you make conclusions about whether it's endo or exothermic, you're always going to use the system. So we make observations about the surroundings, easy to measure temperature of water. So the water temperature went up. That means the system released energy. So we call this process, releasing energy, exothermic. So then the reverse is true. If the temperature of the surroundings goes down, that means the system must have absorbed energy from the surroundings or stolen it. So that means endothermic. So important, again, when you go home and you go to sleep, exo is releasing energy, negative delta H. Endo is absorbing energy, positive delta H, until somebody comes and says, please be quiet and go to sleep, okay? So many times over and over again. So you'll be given the heat capacity of water, but it is important to do final minus initial temperature, or if you prefer numbers like T2 minus T1, that's fine too. But because it's going to influence the sign, it's important to do final minus initial, okay? And then solid system mass over molar mass, volume of water is equal to the mass of water. So in the next block, we're going to look at what happens when you have two solutions. In the next box, I guess. Okay. So it looks almost the same, except it says aqueous. I've set an acid and a base as an example, so it doesn't really matter. You can just call it solution 2 and solution 1. So when you have two solutions, it's not like they're separated, but I'm going to use the separated picture to help us with our math, okay? So the system is the two solutions reacting together, the reacting particles. But then how do we figure out how much water or how much aqueous solution we have? So I'm going to pretend like these amounts are different. So let's say we have 10 milliliters, solution 1, and 20 milliliters of solution 2. So one more time, when you have an aqueous solution, the particles dissolve in the water because they fit in between the water molecules. The volume doesn't change. The what's it called? The density doesn't change. Specific heat capacity doesn't change. So if we have solution 1, which is 10 milliliters, and solution 2, which is 20 milliliters, how much aqueousness or how much solution do we have total? 30. So that means technically we have 30 milliliters of water with particles inside, in between the water molecules, but all we're looking for is the total here. So when you have a question that has two solutions, in order to figure out how much surroundings there is, you have to add them together. And it makes sense. If you put two solutions together and mix them, now the whole amount of volume has particles reacting. So it's not like it's not like it's really like this and then you stick your thermometer in solution 1 and then down. That's not how it works, right? We mix it together. So we want the temperature of the whole amount. So all of the aqueousness, and that is a word. So there are some differences when you do a solution. So I'll write it up here so the people at the back can see. You can put it wherever you want to in your box. So for a solution, moles is concentration times volume. An unfortunate idiosyncrasy of the English language. Big C and little c look very similar. So this is big C is concentration or moles per liter, which means that volume has to be liters. Okay, that's one way that usually the volume is not given in liters. Again, to be practical, our graduated cylinders measure milliliters, not liters. But then, and the volume, we need the total, so you have to add them together. There will only be two. But we're maintaining the property that milliliters equals grams. Same C. Same delta T. And the temperature change notes are the same. So you can either rewrite them in this box or just write You're okay. I'm literally teaching. So sorry. Yes. Have a good weekend. Okay, so the next slide has assumptions. Now, sometimes, there's that cliche, assuming something makes out of an ass out of you and me, right? But like I said, these assumptions are good, and we can easily prove that the first law of thermodynamics holds. So they are good assumptions, okay? Within reason. So the first one says that no heat is transferred between the calorimeter and the environment. So again, if you walk around with your 2 coffee cups like, hey, what's going on? What'd you have for lunch? Then of course there's going to be energy transfer with the environment. But if you do a good job and hold them together, then the first assumption will hold. Secondly, any heat absorbed or released by the calorimeter is negligible. Yes, if we left, hot coffee in a styrofoam cup for hours, eventually it would go cold, but our reactions are going to take minutes, if that. And then, of course, if you have a solution that is proven to be aqueous, usually it's acids or bases, which love water, so they dissolve readily, then you're going to use the same heat capacity, and 1 gram is going to be 1 milliliter. So we're going to do 2 examples. We're going to do a solid system and 2 solutions. So the solid system, there is, if you print to the note off, there's like space here and a box here. The chemical system, I didn't leave a box. So last year, some of my students made it a challenge to write it small enough to fit in there. Otherwise, either write it on the back or on a separate piece of paper, whatever you want, okay? I don't, unless you have the neatest, tiniest handwriting in the universe, then I don't think you're going to fit it there, okay? I apologize. But you can see then I would have one more slide that's so sad, so I guess that's why I cut it off. But the solid one should fit on that sheet fine. Now, if you hate writing with no lines and you want to just put both examples on line paper, you can do that too. It's up to you. Okay, so like I said, as soon as you see in a calorimeter, then your brain should think delta H system equals negative Q surroundings. The other types of questions we are going to do are going to look very different, okay? If it is, yes. I'm just going to write about it, so if you want to like write comments underneath, and then the second slide will do the work. Okay, does that make sense? Again, if you think you can fit it in there, but I'm not going to do any of the math here. So if it's something weird, like this says 10 grams of urea, you don't have to memorize what urea is. I'll give you the formula, so then you can use the periodic table to find its molar mass. You're going to be given the volume of water, so you do need to remember that milliliters equals grams of water, okay? Because this delta H, that's this formula, and the Q formula, you need mass for. So milliliters and grams of water are the same. We can calculate delta T, TF minus TI. So again, it doesn't, the question, if it was on a test or whatever, would say in the question. On the sheet it says, for the following questions, assume the same specific heat capacity as water, or it's on page 306. You don't need to memorize that, but you'll see that every single type of calorimeter question, the C value is going to be 4.18, so there's a very good chance that you probably will have it memorized. When you get to the last line, that is what the clue is, as usual, what you're trying to do. You are trying to find the molar enthalpy. So what that means is molar enthalpy, we're looking for joules or kilojoules, but when you have grams, it'll be joules. Like I said, if I'm looking to sneak in an extra mark, then I'll make you change it to kilojoules. But you're looking for how many joules per mole. Sometimes it'll say just calculate the molar enthalpy for the urea. It says of solution. So instead of X here, I'm going to put delta H sol, but you can put, because I don't want to write the word solution, you can write the whole word, you can leave it X, you can write delta H S, it doesn't matter. Delta H Jamie, okay, whatever you want. But it is here, so if it helps you, molar enthalpy of solution, then you'll know, what am I looking for? The delta H solution. Yes. Urea. That's what this is. Or urea, which is a component in urine. But if it's something weird like that, I don't expect you to know what urea looks like. I'll give you the formula. So whatever the fuel is, it could be, we're going to do like ammonium nitrate or whatever. You'll look at the formula and find the molar mass. Okay, so I'm going to organize my information, my question in a very particular way. So I'm going to basically have a system and surroundings column, and then I'm going to put them together. Okay, so maybe it's not obvious what the system is, but the surroundings should always be water. There is a bunch of ways to figure this out. Whatever it says in the question, that's the system. When you're doing the delta T, that's for the surroundings, because Q is for the surroundings, which is water. Or you just remember, surroundings is always water, system is whatever you're putting in it. Okay, so there's a bunch of ways to think about that. So 10 grams of urea. Now, so urea is NH2CONH2, so you would have to go through nitrogen's 14. 14 plus 2 hydrogens, so plus 2 plus carbon, which is plus 12. So you would just use, you're definitely going to need your periodic table for this, okay? So you can just trust me that it's 60. It's up to you when you do the molar mass. If you think 2 nitrogens, like if you try to condense it even more, this is trying to show you more of like what the structure looks like. Or you can just go in order. 1 nitrogen plus 2 hydrogens plus carbon plus oxygen. Yes. CONH2. And what else are we looking for the system? The last line says calculate the molar enthalpy of solution. So again, I'm going to call that sol. That's what we're looking for. Okay, we're given 100 that we have 150 milliliters of water. So right away, like these questions are virtually identical. So you might just automatically write down that that's the mass because that's what we need to use. So some people don't even write this. Or they don't write this, whoops, and then they just put it in the question as 150, and that's totally fine too. Okay, it doesn't really matter. The C would be given to you, specific heat capacity. So the temperature gets colder. 16.7 is less than 20.4. So you should get a negative delta T. And that negative is important. Please don't just take the absolute value. Okay, so now I'm just going to make it stand out, so I'm going to change colors, okay? Now we are ready to go. We have, as soon as you see calorimeter, delta H system equals negative Q surroundings. What's delta H? N delta H. Again, you can use X or you can put a descriptor. Don't forget this negative. I made a terrible negative. So you decide for yourself. Do you want to rearrange using the variables? Do you want to plug the numbers in and then rearrange it? Doesn't matter. So the mole amount we already found, 0.167. We already said we don't know what this is. We have 150 grams. .18, negative 3.7. You can decide for yourself what kind of relationship you have with your calculator. But most calculators, at the very minimum, unless you use brackets, you have to do 150 times 4.18 times negative 3.7 times negative 1, push equals, and then divide. Okay, so, or you can use brackets, or you can show all of your work, okay? Which I'll do that here. So 150 times 4.18 times negative 3.7 is negative 2,319.9. If you are a dimensional analysis kind of person, so grams cancel, degrees Celsius cancels, so you're left with joules. Okay? To get rid of the 0.6167, you divide. And when we get our number, we're left with joules per mole. Is that what we want? Yes, it is. And then this one cancels over here. So this is like negative, negative, which is positive. So if you're asked for kilojoules, just divide by 1,000. Some of the answers, for whatever reason, I started to get ruthless and I put them in kilojoules. So, and I have no defense for it. So sorry, but there it is. You can think about the logic of your answer. The water got colder, which means the system absorbed energy. Absorbing energy is endothermic, which is positive. Did we get a positive delta H value? We sure did. Okay, so chances are you're correct. One more example. Okay, I cheated and made it smaller, but I really don't think there's any way you can fit it on there. I'm sorry. Unless you have beautiful, tiny handwriting. So this time we're going to do one that's two solutions. So the difference in how you calculate moles is the big one, and that you have to add the volumes together, okay? So a lab tech adds 43.1 milliliters of concentrated 1.6 molar hydrochloric acid to 100 milliliters of a 0.4 molar solution of sodium hydroxide. So usually one of the solutions or both of the solutions are an acid and a base. The temperature of the solution changes from 19.2 to 21.8. So this time it's gone up, which means the system released energy, so it should be negative exothermic. Calculate the molar enthalpy of neutralization for HCl. So again, the very last sentence. What are we doing? Molar enthalpy. What's molar enthalpy? Joules per mole. And this time, it is going to matter a little bit. Sometimes what they'll do to try to make these questions easier is to make the concentration and the volume the same. So then when you go to calculate moles, it doesn't matter which one's the system. If it does matter, like this one, then just look at what the question specifically says, okay? And like I said, in these questions, like on the worksheet, on a test, on a quiz, even in a normal semester, it'll say in a calorimeter, in a calorimeter, in a calorimeter. So if you want to sneak that in there. I promise that I will be as transparent as possible, okay? So it'll say, in a calorimeter, using Hess's law, using standard enthalpies of formation. Okay, so now our system is HCl. So we have moles per liter, which is big C. Nowhere is there grams, right? So it's not a solid this time, it's not a mass. Volume is 100. Milliliters, which has to be liters. So moles per liter and milliliters, they don't match. They don't cancel out, right? So you have to divide by 1,000 to get liters. Maybe you think of it like moving the decimal place 3 spots, whatever works for you, okay? Normally what happens if you forget, you'll get like 3 times, like it'll be 3 decimal places the other way. So let's say we did this. Oops, that's not there. Sorry. Sorry guys, 43.1. So if you forgot to change it to liters, then you would get 68.96 moles. That's a lot of moles. We don't usually deal with moles that big, right? So hopefully that's your clue. Oh, that doesn't make sense. I made a mistake. We are looking for the molar enthalpy of neutralization. That's what the question says. Okay, the last line. So I'm going to call it neut. Again, put whatever you want. Doesn't matter. So we have to do all the aqueousness. So volume 1, 43.1. Volume 2 is 100. So the total is 143.1. Which is the same as mass. So again, these questions are not that difficult. You might just start writing it as grams, or you might just plug it in and not even worry about writing it as grams, which is totally fine. Same thing with delta T. Lots of people will stop showing their work, which is fine here. Just as long as you remember to do TF minus TI. I want to save some room. So I'm going to put 2 equal signs on a line. Don't tell me it's too hard. Some people won't even show the formulas, like they'll just plug in their numbers. You can do that too, start to do that too. again, we have joules, grams cancel, degrees Celsius cancels. We're left with joules. We're going to divide by moles. That's perfect. That's what we want. If you have an affinity for kilojoules instead of joules, and you put your answer in kilojoules all the time, I'll never take marks off, okay? So you'll never lose marks for doing more work. Grade 11 cow. I can't even talk about it. Okay, so first, you have to make sure your lab's handed in. If you want to do the molecule assignment now, that's fine too. You can hand that in. If you don't get those done, just bring them to me next week, no problem, okay? Now, so behind Andrew and Emma in a minute, there's 3 piles of these sheets. These have math practice for this. Both kinds are all the examples we did to this 5.2. It also has, like page 302 is just straight up Q equals MC delta T. It has some of those as well. The 300 and 305 is more about the theory, okay? So when you go to D2L, it says like the 5.1 homework, and there's 2 files, one for the theory and one for the math solutions. On the sheet at the end of the question, it says ANS, and then it gives the answer. So the answers are on the sheet, the solutions are online, okay? So when you're ready, socially distance and go pick up a sheet behind Andrew and Emma, but don't bug them. If you would like to sit quietly at your desk and contemplate life, that's okay too. Just don't be rowdy, but your organic lab should be done. Like, just look at the reactions of hydrocarbons. Use any one of those benzene reactions. Yeah, that's fine. Yeah. Okay, why don't you do taurine? Okay. Yes, there is a Dropbox on D2L as well if you're into that. But yeah, you could just come bring it.